Okay, so we're told something about the population. We're told that human pregnancies are normal, perfectly normal. Here it doesn't say nearly, just a normal model. Mean 266 and standard deviation 16. Part A here asks for what percent of all individual pregnancies last between 270 and 280. They're asking about individuals, not samples. Am I allowed to answer that question? Yes. Because I know the population is normal, I can make predictions about individuals. Part A here, that's a chapter 5 question. We've been doing that for weeks now. That's just taking a normal model, find the z-scores, normal CDF, we're done. We're making predictions about individuals there. So I'm not going to go through it. You guys could do that. Like, that's literally nothing new. Part B, how many days would the top 25% last? That's a percentile question. Inverse norm, x equals e sigma plus mu. You guys could do that. Parts A and B here are just regular old chapter 5 problems. When we get to part C, that's where it gets interesting. Now we're talking about a sample of size 60. So let's start writing some stuff down. So we're told that pregnancy is normal with a mean of, I think it's 266 and a standard deviation of 16. First thing we're going to write down is let mu be the mean length of pregnancy in days. That is a required step, identifying your variable. Then we think we know mu is 266 days, and sigma, the population standard deviation, is 16. Now we want to consider samples of size 60. And we're supposed to check all our conditions. Is this sample that we're looking at purely random from the population? Is it a bias sample? We hope not. Is that sample big enough? Well, since our population's normal, I can use any sample size I want. As long as I'm not bigger than 10% of the population size, I can go as small as I want, though. I could even go to n equals 1. We did it. Right here, parts A and B are asking about n equals 1. I'm allowed to do that because the population's normal. If that said nearly normal, I couldn't answer part A, but maybe I could use a sample of maybe 5. The closer to normal the population is, the smaller you're allowed to make n. If it's normal, n can be 1. It can be anything. If it's not normal, you need n to be a little bigger. If it's not normal at all, then n needs to be probably around 50 is kind of the guideline. Okay, so our n's big enough here. So all possible samples of size 60, the x bars, follow a normal distribution. There'll be questions on test 2 about describing the sampling distribution. This is what I'm asking you to do. Write this sentence right here. The x bars are normally distributed with the mean, the population mean, 266 days, and the standard deviation, sigma divided by square root of n. So that would be 16 divided by square root of 60. Let me throw that in the calculator. Let me pull the calculator up so you can watch me. A lot of times people type this in wrong. So I just want 16 divided by square root of 60, 2.07. Okay, so this, if I ask you for give me the sampling distribution, I mean all of this. Tell me that the X bars are normally distributed. Stop sharing. X bars are normally distributed. Draw a picture if you want. Tell me the mean of that distribution and the standard deviation of that distribution. Notice it's not the same as the population. Okay, now we got this certain obstetrician who claims that his average of this sample of 60, he claims his average is less than 260 days. So we're going to figure out what the probability of getting a sample like that is. We draw our picture. This is all possible samples of size 60 that we're graphing out here, not the population. The average sample would be 266 days. He claims he's down here. Less than 260, wasn't it? Yeah. So we're going to shade below that. We find our z-score. So z is the one we want minus the one in the middle divided by that standard deviation we just found. So I like to do it one step at a time. 260 minus 266 divided by 2.07. Now I'm going to do normal CDF. I shaded below that. So negative 99 to, oh my God, I don't remember what it was, negative 289, I think. I might have to fix this. I think I should have written it down. Yeah, close enough. Like really, I should have rounded that to 2.90, but that's just rounding error. So a very, very small number, 0.0. So this was negative 2.89. And then after normal CDF, we got 0.002. So that's in percentage 0.2%. The probability that this guy's average pregnancy length of this sample of size 60 was less than 260 days is 0.2%. We would write that sentence. Now, what do we think about that? Let's evaluate that claim. For the whole population, the average is 260. If we wanted to find the probability of one pregnancy lasting only 260 days, like we just do regular normal CDS stuff, that wouldn't even be that rare. But this guy claims that he's got 7 or 60 women and his average was that low. That is incredibly rare. Extraordinary claims require extraordinary evidence. Our first thought should be, always your first thought should be, that guy's a liar. If somebody makes an outrageous claim, that's literally why we want you to take this class. That's why you're taking statistics, is to make you a little more skeptical of outrageous claims. Your first thought should be, that guy's a liar. But let's say we went and we checked his records and he's telling the truth. Then our next thought should be, there's something wrong with his sample. His sample does not look like the population. Maybe he works with younger mothers and they give birth earlier. I don't know that to be the case. Don't quote me on that. But maybe there's just something about his sample so that his particular population that he's working with gives birth earlier than the average woman. So that should be our next thought. There's something wrong with the sample. Let's say we check that and his sample does look like the whole population. Well, weird things happen. I mean, if we were to do this same experiment 1,000 times, we would expect, what is it, 5 of the samples to look like this? 5 of the samples out of 1,000 would be roughly in this region. So it happens. Maybe it's just a fluke. Or the other possibility is, we need to keep this in mind, everything we did was based on this assumption right here. Maybe we're wrong about that. Maybe the average length of pregnancy has changed and it's not 266 anymore. But like, that wouldn't be my first go-to. We have plenty of data about how long pregnancies last, right? We have thousands and thousands of years of data. I'm pretty sure we know what we're talking about there.